Okay, in this lecture video we will talk about a procedure called phase estimation, which is quite similar to the quantum Fourier transform. So let's remember the action of the Hadamard transform, which was used in many algorithms. The Hadamard transform can be thought of as an operation which is used to get an information encoded in the relative phases of a state. So let's recall the action of the Hadamard transform on a single qubit x. Hadamard x is basically equal to 1 over square root 2 summation y in 0, 1. It's minus 1 to the power x, y, y. So this is the action of the Hadamard transform on a single qubit. And it can be thought of as an operation which encodes the information about the value of state x into the relative phases between the states, the basis state 0 and 1, right? So since the Hadamard transform is itself inverse, its own inverse, it can also be used as a decoder, decoding the information about the value of x, which was encoded in the relative phases. Okay? So it can also do the inverse process. The n-qubit Hadamard transformation acting on an n-qubit state x has the similar effect. So the n-qubit Hadamard transformation on an arbitrary n-qubit basis state, so let me denote this by plain x instead of using this fancy x for a single qubit. This denotes an n-qubit state, and this is equal to 1 over square root 2 to the n summation plain y, so y is an n-qubit state, minus 1 to the power x times y ket y. Okay, but the phase of this kind is a very restricted form, because in general a phase is a complex number of the form 2 to the e to the 2 pi I theta, okay, where theta is a real number between 0 and 1. Okay, so it's a real value between the closed interval 0 and 1. And actually the phase minus 1 corresponds to when theta is equal to 1 over 2. So the problem here is that when given a phase in this exponential general form, the n-qubit Hadamard transform is unable to fully access the information encoded in more general ways. So we should generalize this transformation to determine the information encoded in relative phases when given the phase in the general form. When the phase is given in the exponential general form. The phase estimation problem can be formulated in terms of another problem called eigenvalue estimation. Okay, so they're practically the same. So eigenvalue estimation problem. An eigenvalue estimation problem is as follows. So given a unitary matrix, call it U, and a quantum state psi, we want to find the phase value theta find the phase theta with high probability and with an amount of small error perhaps, such that u times psi is equal to e to the power 2 pi I theta psi. Okay, so the problem is to find this phase value theta. And this complex number is actually the eigenvalue of the transformation u, okay, where psi is the eigenvector. Okay, so let me give the circuit diagram outright. It's a circuit diagram for the phase estimation algorithm, and let's comment over it as we go. The phase estimation circuit starts with initializing the first register to all zeros. We have 2 registers in total. The first register of the phase estimation circuit holds a number of qubits. Okay. So these are all set to 0. Okay. Let's suppose that this is an n qubit register. Okay. And the number of qubits in the first register really depends on how precise that we want to approximate to the phase value theta. Okay, and with how much probability that we want to measure the correct value in the end. The second register will be psi. It will hold our state psi, the given state psi. Okay. And we will consecutively apply a controlled U gate on the state psi. Okay. Controlled U gates means similar to the C NOT gate. So the first qubit of the controlled U gate would be the control bit, and the second qubit of the transformation is the target bit. Okay. So it's simply the first qubit of the controlled U gate controls whether we will apply the transformation or not. Okay, it's simply the same as a C NOT gate. Okay, so we know that U times psi is equal to e to the power 2 pi I theta psi. Okay. So then the following equality holds in this case. If this is true, then u to the power 2 to the power j, okay, times psi this is equal to u 2 to the power j minus 1 times u times psi, and this is equal to u to the power 2 j minus 1 e to the power 2 pi I theta psi. And if we continue like this, we will end up having e to the 2 pi I to the power j theta times psi. Now assume that we are given a quantum state quantum state 1 over square root n. So we're given a quantum state in a general superposition state from y equals 0 to n minus 1 e to the 2 pi I theta y ket y. Okay, and we assume that theta is a real number between 0 and 1, and also for convenience assume that n is equal to 2 to the n for some natural numbers n, small n. Now what we do next is to apply an n-qubit Hadamard transform on the first register. So we have Hadamard transformation here, we have Hadamard transform here, here. Okay. And then in the output, actually, we have a general superposition state with each with equal amplitudes. Okay. So all the basis states in the superposition will have an equal amplitude, which is 1 over square root n. So this is the state, in fact, after applying the n-qubit Hadamard transform on the first register, the general superposition state. Okay. All right, so then we apply on the first register the inverse of the quantum Fourier transform. I'll fill the rest later. Inverse of quantum Fourier transform, an n-dimensional quantum Fourier transform. And then measure each qubit. All right, so this state, the state after we applied the n-dimensional Hadamard transform, is actually equivalent to the state I'm about to write now. So it's equivalent to the state 1 over, so we assume that n is equal to 2 to the n. So the amplitude is square root 2 to the n. And this state is equal to ket 0. The first qubit is equal to 0 plus e to the power 2 pi I 2 to the n minus 1 theta ket 1. Tensor, the second qubit is ket 0 plus e to the power 2 pi I 2 to the n minus 2 theta 1. Tensor, and then last we have ket 0 plus e to the power 2 pi I 2 to the power 0, that's 1, times theta, ket 1. Okay, so this is simply equal to the state above. Alright, so any number can be expressed in the binary form, and suppose that theta is expressed in the binary form. So suppose theta is expressed in the binary form at 0 point theta 1, theta 2, theta n. And by the way, if you're confused about these parts, you can refer to section 4.5.1 in the lecture notes, and also other texts, of course. But I talk about this, this transformation, the equivalence between this state and this expansion in more detail in the lecture notes, and how to represent a number in the binary form. So you may refer to the lecture notes for further details. Okay, so furthermore, the state above can be written as, if theta is represented in binary form, then this state can be rewritten as one over square root of 2 to the n ket 0 plus e to the 2 pi I 0 point theta n ket 1. So in the first qubit, the phase is just approximated up to the n significant bits. Okay. And then in the second qubit, an extra bit comes up in the phase, so we have a better estimation, plus 2 pi I 0 point theta n minus 1 theta n ket 1. Tensor, if we continue like this, in the last qubit we have ket 0 plus e to the 2 pi I 0 point theta 1, theta 2, up to the last digits, ket 1. Okay, so if we apply the quantum Fourier transform, the inverse of the quantum Fourier transform on this state, and if we measure the first register in the end, then the resultant state will give us an approximation to theta. And let me also complete the whole picture here. Okay, so on the second register, we start with psi, and then we apply a control U gate Okay, so this is the last qubit in the first register acts as the control bit, and here we apply u to the power 2 to the power 0. We just apply u, and here we take this qubit as a control bit, and here we apply u to the power 2 to the power 1. And lastly, we take the first qubit as the control qubit, and here we apply u to the power of 2 to the power n minus 1. Okay, and we have some state u. All right, so given a state 1 over square root to the 2 to the n, from J0 to 2 to the n minus 1 e to the 2 pi I theta j So the inverse of the quantum transform transforms the state to some state theta cap, let's say, and u. Okay, so whenever we measure the first register after the transformation, we get to observe a state theta cap, which is an approximation of the phase value that we want to find, theta. So this is an approximation to the phase value theta. So essentially, phase estimation is practically no different than the eigenvalue estimation problem. Okay, so we have completed the quantum algorithms section, and I'll see you in the next video.